Hello students, in this lecture video I'm going to tell you about the dynamic consideration, that is a dynamic analysis we will study. Okay, along with that we are going to derive the two equations, that is a derivation for the lumped mass matrices and derivation for consistent mass matrices. Okay, these two equations are very much very important to solve the numerical problems on this dynamic consideration. Okay, so here the so far, okay, that is the second half of this syllabus. Okay, formulation of point masses and distributed. Okay, so this we are going to study in this lecture video, that is consistent mass element. Okay, this derivation we are going to study in this lecture video. Okay, so let me understand what you mean by dynamic analysis. Okay, so far we solved about the display. Okay, so what the displacement, stresses, strain, reaction, all those things. Okay, in the dynamic consideration, that is in finite analysis, in the finite element analysis, okay, it is nothing but by considering the variable like such as the displacement, strain, stresses, load as the time independent variable. Okay, so along with the time we are going to derive this all the equations. Okay, that is the finite element analysis is nothing but the dynamic analysis of in a finite element analysis, nothing but the considering the variable like displacement, strain, stresses, load as a time independent variable. That is most important. Okay, along with that time we are going to consider here. Okay, but here since the basic variable displacement vary with the time, that is additional forces, that is the inertia forces and the resisting force we are going to consider while writing the equilibrium equation, what I shown in the picture. Okay, so here we are going to study about with respect to the time variable. Okay, so we know that for the equilibrium equation for the time dependent independent variable, that is in the case of the static. Okay, but whereas in the dynamics, so we are going to it is depend upon the time variable. Okay, that is what the dynamic analysis. Okay, along with that we are going to consider this. Okay, that is the inertia forces and the resisting forces. Okay, that is Ku plus Ma is equal to F. Okay, where M stands for the mass of an element, A stands for the acceleration. Okay, so this is about the dynamic analysis. So just to understand that dynamic analysis is nothing but what we are going to consider the parameter variable that is depending upon the time, that we have to remember. Okay, so now the first derivation, that is derived in lumped mass matrices for the bar element. So this is these two derivations are very much, that is very important to they may appear in the examination. Okay, you have to perfect in the model fifth half. Okay, one derivation for either lumped mass system or the one more is here the consistent mass matrix. Okay, among two anyone they may ask you in the examination. Okay, so here this definition. Okay, so same, consider a 2 bar node bar element. Okay, so this is consider a 2 bar node element. This is the node number 1, this is node number 2. Okay, cross section length area, okay, A, and the mass density rho, which can be moved in the axial direction. Okay, so mass density is given so in the axial direction along the x direction as shown in the below figure. Okay, so this is the node number 1, this is node number 2. Here the q1 and q2 stands for the nodal displacement. Here there is an external, this is an internal. Okay, the force, axial force is acting okay along the x direction. This is the length. Okay, L bar element subjected to a time dependent loads. Okay, this is most important here in the dynamic cases. Okay, that is the time dependent load. Okay, the total mass of a given element is the mass of a total mass is equal to mass density rho Al. Okay, that is the area length. Okay, so this can be divided into two equal parts assigned to the each at node. Okay, so this is the total so this is the total mass element. This you can divide the half of that and place it at node number 1 and at node number 2. Since the bar under the time dependent force according to the using the Newton's second law of motion, each node have okay, at each node we can take the external forces, that is here the external forces. Okay, so E stands for external force is equal to the internal force Fi. Okay, Fe nothing Fi. Okay, and the inertia force, that is mass and time, and for the acceleration. Okay, therefore the force at node number 1, which is given by the external force is equal to external force plus 1 plus internal forces mass density, that is a mass 1 for the lumped mass system for the first node, and d dou square q1 by dou t square with respect to time. So give equation number 1. Okay, similarly at node number 2, at force at node number 2, that is the external force, that is outcoming F2E is equal to 2t, that is the two external forces. Okay, so this is first one is the force equation, that is internal plus external. Okay, so this is the second force at external, this is the internal, this is 2. E stands for the at node number 2 and E stands for the external. Here I stands for the internal plus mass matrices, so dou square q2 by dou t square. Okay, where m and m are the lumped masses and obtained by lumping the total mass of the bar equal divided at the each node. Okay, so that is m1 is equal to mass density rho Al by 2 and m2 is equal to same equation m1 m2 is equal to rho Al by 2. Okay, so this equation number this, and equation number node number this. Okay, so this equation you can write the matrix form. You are going to get f of 1 e is equal to f of at node number 2, which is equal to external plus internal plus m1 0 0 0. So this is dou square q1 by dou t square, dou square q2 q by dou t square. Okay, if you multiply these two means you are going to get the same equation. Okay, so this is what the in the matrix form equation. Okay, so this equation is similar to this equation, that is force is equal to ku plus ma. Okay, so mass and acceleration. Okay, so where k is equal to ae by l, 1 minus 1 minus 1 1 is known as for the stiffness matrix for the bar element, is already we know. But for the lumped mass system, so which is equal to same, so that we are going to consider this one as that is what m is equal to rho density mass density al by 2 1001. Okay, so this equation is known as the lumped mass system for the bar element. Okay, so this equation you have to remember to solve the numerical problems on lumped mass system. That is lumped mass system matrices m is equal to mass density area length by 2 1001. Okay, so this equation you have to remember. Okay, so this is what the first equation, the first derivation. So coming to the second derivation, that is a derive the consistent mass matrix for the bar element. Okay, again the same diagram you have to take. So consider a mass matrix for the bar element, and it can be derived by the various methods such as a variational method, a vibration method, virtual working principle, or minimum potential energy and D'Alembert principle. Any method we can solve, but according to this what we are solved by what according to the D'Alembert principle, most generally are used for to solve this getting the consistent mass matrix. Okay, so for the consider a small strip of a given element, that is the kinetic energy of an element of a mass density rho that occupies the problem domain and moves with a small velocity, that is velocity v n q dot, here the dot is missing. Velocity v of n q dot is given by is equal to kinetic energy is equal to half of this q dot transpose integration of this mass density shape function n into dv by this what the velocity. Okay, so velocity and acceleration. Okay, again you simplify this, half of q transpose is equal to this is equal to mass matrix Radon mass matrix into q dash. Okay, where m is nothing but the element consistent mass matrix. Okay, so consistent mass matrix is different, lumped mass system is different. Okay, don't be confused. Okay, so this which is equation is which is equal to this integration of mass density transpose of that shape function n into dv. Okay, so we know that for the shape function n for a given bar element we have this equation already. We derived this equation for the what the shape function for 2D element, that is a bar element. So n is equal to n1 n2. So n1 nothing but what 1 minus zeta by 2, 1 plus zeta by 2. These are the standard value for the shape function for the bar element. Okay, so n transpose we have in the equation, so n transpose is also there. So write this is in a vertical fashion, and elemental strip area integration a into dv nothing but what area into dv. So this equation we can write as integration of minus 1 to plus 1, that is first equation minus 1 to plus 1 is equal to la by 2 d zeta. Okay, so now you substitute that equation into in this equation, that is a consistent mass matrix. So transpose you substitute here also, dv also substitute. Okay, so after substituting you are going to get this equation, that is consistent mass matrix is equal to density rho a la by 2 minus 1 plus 1 n transpose n into d zeta. Okay, so again you simplify this. Okay, substitute here transpose n zeta and n zeta. Okay, so after substituting n here you are going to get this, and multiply this equation you are going to get the consistent mass matrix for the shape function, which is equal to mass density area length by 6 2112. Okay, so this equation you are going to call as consistent mass matrix for the given bar element. Okay, so this equation mass matrices, that is a consistent mass matrix, and this equation you have to remember this. Okay, so lumped mass matrices. Okay, lumped mass matrix equation is m is equal to rho a l by 2 1001. So here consistent that is consistent mass matrix nothing but what rho a l by 6 is there. Okay, so here what 2 is there. So here 1001 in that side, here 2112. Okay, so these two equations are very important to solve the numerical problems on what what the dynamic consideration or dynamic analysis problem. Okay, so we have to remember these two equations. Okay, so that is here the consistent mass matrix means density, the given bar element or the given metal property density will make constant, that is they may give some values. Area, okay, so area also they may give. Suppose if area is not given, means let us assume area is equal to 1 meter square and length of the given bar element they give 62112. Okay, so this equation you have to remember, that is consistent mass matrix equation for the bar element which. Okay, here thing is you have to remember this equation first, that is the kinetic energy of a given small element equal to this equation you have to remember. Okay, so where half of q transpose, that is the velocity q transpose me q dash. Okay, so this equation, okay, this mass matrix which is equal to this integration of mass density into n transpose into t dv. Okay, so now we have the standard formula, that is shape function, is substitute in this equation, so you are going to get that values. Okay, So this is most important derivation. Both are very very important for the point of examination. Okay, so I think I hope you understand this. Okay, thank you.